So, hi everyone. For this episode, what I want to be talking about is how to do distributed training in Pytorch. So, there's a couple of paradigms for how to do this. Generally, let me zoom out a bit more here. So, there's a couple of paradigms for how to do this, and I have talked about them a bunch before. Like, you have data parallel training, which is you have a model that fits in the memory of a single device, but then you pass it different subsections of the data, and then you merge them in some way. There is a model parallel, which is a single model doesn't fit on a single device, so then the layers sort of need to communicate with each other. But I sort of never talked about how this actually works, right? Like, because you do have multiple machines running, possibly different operating systems with like different PyTorch runtime. So how does this work exactly? Just like SSH into every machine, and when they're sending stuff to each other, well, how do you send it? Like, what happens if a machine fails? And so there's lots of stuff we sort of brushed under the rug in that last video, and so I think I thought it'd be helpful to just rediscuss how this actually works, right? And so I think the main things we're going to be discussing today is data parallel training, which is the paradigm I just described. RPC based training, which is a remote, which stands for a remote procedure call. So you're going to basically call a function on another machine. And then we're going to talk about collective communication libraries. So basically, really the main things you need to worry about here are all reduce and all gather, which are basically either aggregating some data, like let's say a sum as a reduce, for example, of various vectors. So this is, and then gather is basically getting, for example, all the like gradient updates from several machines and gathering them into a single gradient update that you then synchronize across everyone. So that's an all gather, and then obviously like the sending part, which is well, once you've aggregated them, well, how do you send back these gradient updates to everyone at the same time? So this is what send and I send are about, right? So, um, but I guess like before we get into this, like I thought it'd be helpful to just go over another example of data parallel training. And so I actually really like this sort of like upgrading chart here. But basically, if you're just starting out and you don't even feel like scale is an issue, like I don't know, you're just waiting for a couple of hours to get a model output, then you probably don't need data parallel training. And so in this case, like this is not really a real concern. The second thing to keep in mind is like, well, let's say you're provisioning something like an AWS cluster, right? Well, in that case, typically you can't just get a single GPU. Well, you have a single GPU if you have a gaming machine, for example. But if you're using AWS, like typically you're provisioning 8 GPUs at once. And so you don't want to be using one GPU at a time. You want to use all 8. And so what you want to use here is basically this is what's called data parallel. And the interesting thing about data parallel is that when you're saying, well, I have a network, you then say, okay, I want this to be on the following device IDs. And remember, if you're using 8 GPUs, these are going to go from 0 to 7. And so if you just put 0 to 7, now you basically just have a distributed model that works on 8 GPUs at once. That's it, right? Like this is kind of crazy, right? Like the fact that this is pretty much the only code change you need to do. But it's sort of like the benefit of using something like an AWS cluster, because they'll have these device IDs allocated to different ideas for you automatically, so you don't need to do much, right? So that's data parallel. And now if we go to the next step is saying, well, single machine. Okay, so let's say you want to write a bit more code for this, and then there's distributed data parallel. And so what do they do exactly? Okay, this looks identical to the previous one, so I don't see any substantial difference here. Okay, distributed data parallel. Okay, I see. Let's see what the so it has like a bit more stuff going on. So it has like the IDs. It has this output device, gradient as bucket cap. What are these bucket caps? Let's quickly look at. Uh, okay, oh yeah, perfect. We can take a look at some code. So for example, here they're allocating these two 3 by 3 tensors, and then we're going to make a remote procedure call on the first worker where we're going to make an addition. And then the arguments for this addition are T1 and T2. And then we have this distributed model here, which is fine. We just said DDP, where DDP is basically this distributed data parallel. And then we basically say, well, okay, do the optimization. This is gradient descent. And then here, instead of like the regular context loop, you're saying with autograd context as context ID. And I would imagine this is just like a way of running a job per machine. So depending on the context that you're in or the GPU that you're in. Otherwise, this again, this looks the same, right? Like you have a model, the prediction of your model, you have a loss function, which is a function of both your prediction and your loss, and then you make the backwards pass, which is a function of the context that you're in and your loss, and then you may take a step forward here. So this is all like just traditional stuff, and what we've basically just done is change uh, optimizer to distributed optimizer, param to distributed param, like model param, and then we're doing this weird RPC call. So we'll just sort of get to these in a second. One thing that I thought was hilarious is how many warnings there are. Like there's a ton of warnings here, and I think it's just generally because whenever you're doing distributed systems, the first that people just discourage you from doing it because it's hard. You deal with concurrency issues like failure. So generally, I mean, if you don't need to do it, why bother doing it? Um, so let's, I mean, just take a quick look at what are the arguments here because I think it makes it a bit clearer what's going on. So the output device, okay, for multi-device model, speed model must be none, and the module itself dictates the output location. Okay, that's fine. So this is the device ideas. Okay, so we talked about that. Flag that enables syncing of the module at the beginning of the forward function. Uh, okay, for distributed data all reduction. Okay, bucket parameters into multiple buckets so that gradient of each bucket can potentially overlap with backwards computation. Um, oh, interesting. So this is the bucket size, bucket parameters into small, so that gradient reduction for each bucket. Okay, so this looks like some way of controlling, like, what can you update while you're doing your backwards pass? This is interesting. I'm not really exactly sure what it does yet, but let's just keep going. Unused parameters. Okay, you can also mark some parameters explicitly as, don't compute gradients for them. Okay, this is deprecated. It's very useful. Uh, Towards distributed init process backend and CCL. Um, I think this is interesting to mention. Let's talk about this for a second. So typically, when you're deciding, like, what's your protocol basically on which you're doing this sort of distributed training, NCCL is a sort of popular backend, but there's like a couple more. Yeah, so here there's Glue that's useful. I use Infiniband. So let's just quickly Google this and you'll see what I mean. NCCL. So it's the NVIDIA Collective Communication Library, and it implements multi-GPU and multi-node communication optimized for NVIDIA GPUs. Okay, and so what's Glue? Okay, so it's interesting. Like they have a couple of different interfaces. Like one is Glue, one is MPI, one's NCCL. And let's just take a quick look of what seems to be the best, right? So they're using NCCL, and then doesn't do anything for CPU, right? Because NCCL is just it's the NVIDIA library. So it seems to work great for this. And then you can't send and receive stuff, but yeah, I guess this is sending and receiving to the accelerator, right? Since it's not communicating to the CPU, it's not going to have this. Whereas here, it's like, okay, well, they have this reduced scatter, this all to all. There's no all to all. CPUs have all to all, just only on MPI. It's interesting. I don't know what barrier is. I think it's like a way to force a sync at a certain point. Gather, scatter, and then an all reduce. So yeah, so again, gather is getting data, scatter is like giving that data to several points at once. Uh, Broadcast is given a single point. So these are all communication patterns that determine on how, like basically, think of it like there's two steps, right? One is who's doing the communication, and then step two is to how many nodes are you doing the communication. So this is where the names come in, whether it's like all to all, and all to all basically means any any node can talk to any other node. Um, so that's generally slow. That's why people don't do it much. Um, let's see here. What's Infiniband again? So it's a computer networking communication standard used in high performance computing that features very high throughput and very low latency, and it is used for data interconnect among and within computers. Interesting. Okay, so it looks like it's a data center protocol that's independent of NVIDIA's. Is a bit, I guess, like a bit more general, probably not as fast. Uh, okay, so they're saying which one should we use for GPU? Use NCCL. Okay, and then use Glue for CPU training. Okay, and looks like they're not recommending MPI at all. I think these are all interesting, right? So like again, when you're thinking, let's just quickly skim these functions because it gives you a good idea of like what to expect from the stuff. So here, TCP store, distributed key value store implementation and the holds data. Okay, yeah. So why would you need a key value store, right? Like let's say you're storing like data, right? Like not model, it's just data. And you have like the data and it has like a key value store. Like let's say it's for example, just like make this concrete, like it's a reinforcement learning use case and you have the state is your key and then the value is the reward you got at that state, right? And so now you're basically sending data back and forth from the store to multiple machines at once and orchestrating these data transfers, making sure that data gets resent if it gets lost, that it gets to everyone. So this is why you would need an abstraction for this. Hash store is sort of similar, and then file store also, this also looks like a key value store. Um, store. Okay, let's wait. Okay, so this looks like just like a way to basically you're saying I need to get this data, otherwise I'm going to throw an error. And so like if you're dealing with stuff like where I guess like you have asset transactions or something that has to be committed, this is where this stuff could be really useful. What else is here? Distributed store, set timeout, sure. Okay, groups. So what are groups? So by default, collectives operate on the default group called the world and requires all processes to enter the distributed function call. However, some workloads can benefit from more fine-grained communication. This is where distributed groups come into play. Uh, okay, I still don't understand what this does, by the way. The world. Okay, this looks a bit more straightforward, right? It's like you're sending data either synchronously or asynchronously. That's great, right? I mean, synchronously means you're waiting to for the sender to for the transfer to finish. Otherwise, just keep going on with your day-to-day job. Like it's not gonna block when you make this call, so you keep going. Okay, so let's look at an example here. So one, we're gonna initialize a process group, and then the world size of 2. Okay, sure. So we create a tensor, and then we move it to the GPU. We create a stream, and then we do distributed all reduce on output, which is the, we're not, yeah, just the output. We're not using the stream yet. We basically wait to make sure everything's complete. And then we're going to wait on the stream and then we're going to add to it 100. So what does rank mean? If the explicit call to wait stream was omitted, the output below will be non-deterministically 1 or 101, depending on whether the all reduce overwrote the value after the add completed. So what does rank really mean here? If rank, where is it? Rank. Uh, no, it's not a matrix rank. It's something a bit different. Okay, let's just keep going. Maybe this will make sense in a bit. So I guess like group is an abstraction for like a collection of machines that are together. So send the data not to this machine, but to this group of machines is what I would imagine they mean here. Um, okay, sure. And the all gather collectives, let's provide an async op. Yeah, so reduce is basically, think of it like a sum, max. So any operation that actually reduces the amount of data with via some aggregation, where the aggregation function is in sum, max, min. These are all reduces. Okay, let's take a look at this. So you have, I don't know, you have a tensor list. So you have a list of tensors. So there's two of them, and we're gonna give them a rank 0 and 1, and then we're gonna say, I mean, where is this rank defined? They just keep using it like this. Um, Fine. And then they're saying all gather the tensor list. So one, two, three, four. Okay. So I guess like all gather means provide this data to all of the machines, right? So, and by machines, really, I guess it's a bit more abstract than that, right? Because like you have a tensor list, and this tensor list has both. It sounds like it contains both the actual data and the data on and the machine that it's on. So I would imagine that that's where this is really coming from. Okay, so that's where the all gather comes in, and then generates a list of tensors in a single process. Sure, yeah. Instead of an all gather, it's just a gather, right? So like this makes sense. There's an example of a scatter, yeah. So scatter is a list of tensors to all processes in a group, right? So each process will receive exactly one tensor and stores data in the tensor argument. Uh, oh, interesting. Yeah. So it's not a machine, right? It's just a process that's holding some data, and then the process itself can be on any machine, or they could all be on the same machine. Like that doesn't matter. It just depends on how many processes you can run at once. Yeah. So again, so gather is yeah. So and then given gather and scatter, you can build something like reduce scatter, right? Which is just doing one after the other. So you can build these higher level functions with this. So nothing too surprising here. Yeah, barrier, as I suspected, synchronizes all the processes. Like in case again, let's say you're doing you want to synchronize weights of, let's say you're doing data parallel training, right? And you have 10 processes that are running the model, and then after 1,000 epochs, you want to just make sure that everyone synchronizes their weights. So you can basically say, well, after if epochs equal, if epochs is modulo 1,000, then I want you to do torch distributed barrier and synchronize all the weights before you keep going. So the reduced ops here is like what we talked about, right? So you have the sum, product, min, max, so product of everything, the sum of everything, min, max. I don't know what band and bore are. What are band and bore? Okay, they're not available. Oh, binary and binary or binary XOR, right? So these are all operations that would turn it into a single Boolean value for everything. Towards this without reduce op and then reduce op. Okay, so they're saying reduce op is recommended to use instead. Okay, so this just looks like it has more stuff, but maybe just for some backwards compatibility reasons, they still have this stuff. Um, so if you want to use collective communication supporting autograd, you find implementation of those in Torch distributed NN modules. So let's say multi-GPU collective functions. Uh, all reduce, all gather, reduce, scatter. All right, so what's the difference between broadcast and scatter? Difference between broadcast and scatter. Okay, broadcast sends the same piece of data to all processes, while scatter sends chunks of an array to different processes. Okay, who's the best? Okay, so it's just a question of like they're kind of the same, but it's just a question of like is you just have one big chunk of data or not. So I think they say the same thing here. So this is the MPI interface. It sends the same piece of data to everyone, while MPI scatter sends each process a part of the input array. And broadcast is the opposite of reduce, and MPI scatter is the opposite of MPI scatter. I think I've seen this tutorial before. I think I've read it in English, perhaps. Yeah, I've seen this tutorial before. But yeah, I mean, effectively, it's just it's interesting to look at because I mean, it's it's funny that's still probably understandable even in Mandarin. But like if you just look at the interface, it's saying, well, you have a function that sends data, right? You have some sort of send count, a pointer to data that's received, some way to keep track of how much data was received, the data type of what's received, and then a communicator. So you can sort of get a good idea of what's going on here just like by looking at the abstract interface. Even if you don't understand C, like just is it a pointer to something or is it something? It gives you a pretty good idea of what's going on. I think like these are interesting pictures. Yeah, so they actually show like the broadcast sends the same data versus here it's sending multiple chunks of one piece of data. With the gather, you can see here it's like creating like basically let's say for example this was a four-layer neural network. And before you can actually make an inference, you need to get those four layers. So this would be a gather operation. And then an all gather would be, well, let's say you're doing distributed inference, as in you have five machines that each need to do inferences live on some data by users. Like let's say it's a ranker or something. And so after training the model, then you need to basically deploy the model on 10 different machines. And so you would use something like an all gather. And so again, think of it this way. Like, I mean, like MPI exists, right? But you know, like you don't want to be using like something like C++ to deploy a model. You'd rather use like some higher level abstractions in Python, and so that's really where I think the Python MPI interface comes in. That's where glue comes in if you're using distributed CPU training, which you may not necessarily need that, but if you're doing distributed GPU training or inference, which you know, it's probably likely that you'll use, I think something like NCCL, the NVIDIA Collective Communication Language or something would be very useful. So this is sort of like where all of this stuff is coming in, right? And so again, I think maybe I'll keep track of this tutorial. Like just let me bookmark it. I'll add it to the references because I think this looks like a good one. Was Kendall? Oh, I already started this. Okay, cool. Good job, past Mark. Okay, so these multi-GPU collective functions. So check this out, right? So you're saying like this is the backend, and then this is the method I want you to initialize, and there's like world size and then the rank. And so I'm not too sure what both of these mean, like world size or rank. Um, but we can get to it in a second. I think let's just go back to the this main tutorial. Uh, so world size distributed by Deutsch. Excellent. Someone already had a question. So when I was learning Torch distributed, I was also confused by the terms. I think group should be understood correctly first. It can be thought of as a group of processes or world. And one job is corresponding to one group, usually world size, is the number of processes in this group, which is also the number of processes participating in the job. And rank is a unique idea for each process in the group. I see. Okay, so I think this somewhat explains it, right? So, like I said, world size is the number of processes in a group. A group is where was it? And where it should be we thought of as a group of processes, right? So a group is a group of processes. They could be on multiple machines. A world size is the number of processes in each group. So basically, let's say you can have 10 processes run on a machine. Then you have a group ID, and then the world size is 10 because you have 10 processes. And then to indicate each process, you would have 10. So for example, this gets interesting where, well, in your code, you could say something like if rank is equal to 0, for example, then do an all gather, for example, to basically end because you're doing the inference actually on machine 0. And so this lets you control basically, I think you could have the same code running on every single machine, but then it only changes based on if but you say if rank, and then you can run some if rank equals something and then run some specific code to that. And I think this sort of like helps simplify how a lot of this stuff works. All right, so this is great, and it looks like these concepts are coming from MPI. So these are not abstractions that Pytorch created. Like these seem to have existed before. Right. So okay. So this was a big digression, but again, like and remember that if you're just doing something, if you just have like an AWS GPU, like I mean, I think it's very unlikely that you'll even use more than 8 NVIDIA GPUs for anything. Like I mean, like maybe you will like maybe at your day job or something, but at least for like side projects, I don't see anyone using more than 8 GPUs for anything. So just using regular data parallel is probably going to give you amazing returns. Um, so they also talk about this launching script. So let's take a quick look at this thing. Um, yeah, so let's take a quick look at this. So imagine you're running some sort of data parallel operation. And so you're running, like I said, the same script, right? Because it's the same code that's going to be running on all the machines. And so it's train.py. And then for each node, you basically have a collection of groups. So let's say that this group is called 0, and then this group is called 1. And it could be that the first group, for example, manages like the first half of the model, or maybe they do training, and this other one, like, no, so these are all doing training. And so then you need a way to index into the group, and then given, and in this group, you need a way to index into the specific GPU, and then within the specific GPU, you need a way to index into the specific process. So it's just like it's indices all the way down. And so I think in this case, they're saying like there's two nodes, and two nodes, I think I would understand this as two different machines. And within each machine, you have basically two groups of nodes, and within each group of nodes, you have two GPUs. So again, you need a way to index into all of them. And so I think the interesting thing here is that they're saying, well, to launch it, uh, let's see, what do they do exactly? So they're saying from OS path, import path, and then print path, join torch file, and then they're run distributed launch.py. And this will print, it passes the world size, global rank, and mass report via environment variables. Okay, yeah. So this is not like, crazy. Like essentially the way this would work is that here, actually, yeah, it's here, right? So actually, this is just printing stuff. And it's gonna basically have an environment dictionary. And what this environment dictionary is gonna have is it's gonna have a reference to what is the main or the master node in this case. And so the master node is gonna keep track of like what is the size of the world, like how many processes can you run on each node, and then where is the main node, and then each follower node needs to keep track of what the main node is, and the way it keeps track of it is just a key value store that you would that you would just instantiate in this way. And so then basically this also comes like a sort of a DevOps exercise, right? Where on each node that you're running this, you need to make sure that the follower nodes actually can make a call to the main node. And so basically just like looking at a regular AWS tutorial, I think would help a lot. But let's say here, for example, they're saying, okay, we have this like we have a local world size and a local rank. So this is on each group of GPUs, and they're gonna say, okay, n is the rank one uses GPUs this, and then rank two uses GPUs. So remember, rank is just an indexing mechanism. And then, okay, so we have this n and we have these device IDs. That's great. And then, so for the model here, we're saying, well, we're going to run this model on device IDs 0. And then because device IDs is a list of a range of local rank, I'm not sure what this is doing exactly. Let's just skip ahead for a sec. And then we're saying, okay, we're going to take the MSC loss over this list of device IDs. But here we're giving everything. Uh, and then we're going to take the loss, we're going to optimize it, and then we're going to zero the gradient. So just start from scratch. Then we're going to look at it and output, take the loss of this random output. So this is like a random loss. So we're just taking like a random loss and updating the optimizer. Oh, I see. So this is the script I was talking about. So the application can be launched via launch.py as follows on an 8 GPU node with one process per GPU. So remember, this is the simplest case for doing distributed GPU training because, like I said, AWS provides you with 8 GPUs if you're buying any sort of GPU instance. And so 8 is sort of the default. And so I think this is sort of a single machine example. Yeah, you can use this, but I mean, if you are doing a single machine thing, I would just recommend you use GPU data parallel and not worry about any of this because you're just like you're gonna muck around with this like way too much, I think. At least that's what I would do. I'm not saying things that I wouldn't do myself. Um, Yeah, I mean, they're saying like, look, this is error prone, and it is, right? Because for each node, you're saying like, can each node see this node here, for example? They're even setting up like the master address as local host, and which is again the simplest case. But if this is a URL, then you need to worry about like can the nodes actually talk to each other via HTTP? So it's like another thing to keep in mind that may be error prone. Um, so let's just like here like we talked quite a bit about data parallel training. I think I also thought was interesting was they talk here about Torch Elastic. Let me just quickly show you what this is about. Uh, so imagine now that your nodes, let's say you're running over hundreds of nodes, then it's very likely that any one of these nodes could fail, that they disappear, that they have some sort of issue. And so being able to elastically increase the amount of processing that you need, which is something that web dev people are very used to. Like, let's say you would just say something like, well, if number of concurrent clients is above this threshold, allocate more servers that do the exact same thing. So this is very similar. Like, you're just like want to elastically increase the training if the machines are being throttled. And then the other aspect to keep in mind is that, well, if any of the machines disappear, you could just allocate a new one, or like allocate it from a bunch of other jobs. So this is sort of like the main idea. It's like typically people have nice, good scripts for that. Like you're giving like see here the training script with the arguments and endpoint, the backend. Um, so this is just something to keep in mind. Although I don't know many people who actually do this. So let's check this out for a second. Distributed RPC framework. Okay. So let's look at an example. RPC. Yeah. So here, for example, they're just taking the simplest example, like a torch.add. But I'm curious, like, if there's something a bit higher level that they cover here. It's just all ads, it looks like. Yeah, another thing to keep in mind is that if you ran a remote protocol, you need just a way to access the data that it generated. So then you need a remote reference because it's not running on your machine. JIT everything and get some worker info. So this is pretty high level still. Like, I mean, it doesn't like really like it's not like training is necessarily like different because you still have a computational graph on which you're doing backprop. But I guess I would like to see maybe in another video an example of how to actually do distributed training with this thing. Because like yeah, I mean addition is great, but it doesn't really tell me how this stuff actually works. Um, so what is this backend thing? RPC backend init method. Yeah, so just addition. So again, remember this idea with world sizes, nothing crazy. Yeah, it's remote referenced on a remote worker. So yeah, so let's say like you don't want to actually gather or scatter anything, that you just want to like access it, then a remote reference could be a good abstraction to use. Okay, so this is distributed autograd. Yeah, this is a bit more interesting. So let's say you had two tensors, and then you're saying I want to do an addition, and then I want to reduce. So yeah, so I want to reduce, and then I want to just take the sum of the result, right? So I just want to get a like a value. So that's what the loss is, right? And then I want to take the gradient of this loss, and then that's a function of your context ID, which is which machine are you in, and then it looks like a list of losses, right? Because like let's say you have multiple context IDs. I think this is why this is a list, or if it's like a maybe it's like a more general loss function, like let's say it's a multi-loss function, then this would make sense why it would be a list. I don't know though, like maybe if you just give it loss without it being a list, it would still work probably just fine. But I don't know, I would need to try it out. Okay, this is all fine for now. Like, let's see here. So maybe let's talk about collective communication for a second, because I think we did distributed parallel training, right? We talked about this is sort of the vanilla distributed hello world training because nothing's talking to each other. They're only syncing weights occasionally so that you're not losing too much work. The distributed RPC framework we talked about, it's basically a way to make a remote procedure call on a different machine. Uh, and then this framework basically, yeah, so it includes facilities for making a remote procedure call, having a reference to data, so code or data. And then it gives you a good way to basically do automatic differentiation across code or a computational graph that exists over multiple machines, and being able to actually find the gradient with respect to this graph and then optimize it, right? So this is what this whole distributed RPC framework is doing. So now with the distributed communications packages, I think we already covered this, but basically they're sort of free frameworks. Like one is NCCL, which is NVIDIA's, which is great if you're using GPUs, Glue, which is great if you're doing anything on CPU, and then MPI. And so maybe because these look almost so MPI doesn't do anything for GPUs, it looks like, and neither does Glue. And so let's just look at MPI versus Glue, and I think we should be good for today. Okay, so interesting. So Glue was also by Facebook itself. It's comes with a number of collective algorithms. They include a barrier, broadcast, and all reuse. right? So remember, we talked about these quite a bit. Um, so the IP can be used at all times or Infiniband when available. Yeah. So basically, there's two ways. Like think of it this way. Like I mean, if you're running this in a data center, you're not going to talk over IP. All right, you're just going to use Infiniband because it's just going to be faster. If you have GPUs, you're going to use NCCL. That's going to be even faster, like the NVIDIA Collective Communication Protocol. Otherwise, if this is like distributed across the internet or across multiple machines, then that's when you would default to something like IP. But that sort of wants to be like that's the worst case scenario, right? Because this like internet is slow, speed of light isn't fast enough. So for these kinds of use cases, um, so that's cool. I mean, do they compare this versus MPI? Let me see. Oh, it's dependent on MPI, so it's one of the requirements. Um, but it looks like when should I use both then? MPI versus glue. So is this a team? The Horvath team. Distributed training for TensorFlow, Keras, Pytorch, Apache. Yeah. So again, remember, like these guys are very likely to just be using one of these protocols, like MPI, Glue, and CCL, calling them in the appropriate way, deciding whether it's going to be IP, whether it's going to be same InfiniBand, or whether it's going to be the NVIDIA communication protocol. Otherwise, it's going to be a bunch of if conditions, right? Like in this case. So here, for example, they're saying, okay, well, they benchmarked MPI versus Glue, and it looks like the performance is highly comparable when NCCL is used. But Glue is slower without it. And so, to me at least, looking at this, it seems that maybe Glue is a library that combines both, like it leverages MPI and NCCL depending on when it needs to. Otherwise, I'm assuming it's going to introduce more of an overhead, right? Because it needs to check which domain it's in, whereas MPI is maybe assuming that it's in the distributed training paradigm. So yeah, I mean, I hope you enjoyed this. I think let me quickly go over the where is it Chinese tutorial? Nope. That tutorial was really good actually. Yeah, this one. Okay, so it's called mpitutorial.com. And then MPI tutorial introduction. No, not this. What was the gather? Okay. So really, the main thing I want you to take away from all of this is that whenever you're thinking about distributed training, there's sort of two domains that you're going to be in, like main ones at least. There's a lot more, but these are like I have other videos about the other ones. But really, either you're doing data parallel training, which is the same machine is run, the same model is running on multiple machines, or you're doing a model parallel training where you have different subsets of the model running on different machines at once. And so, depending on which case you're in, like you're basically going to need to aggregate either basically the data that you're working with is either the input data, the output data, the model weights, and the model gradients. So these are the four things that you're sending back and forth whenever you're working with this stuff. So let's say in this case, like I want to broadcast like the same weights to a bunch of machines that are all doing distributed inference. Then using something like a broadcast makes a lot of sense. A scatter makes a lot of sense in the scenario where I want to send different subsets of a data set to different machines. Let's say this is a stream, right? So it's a distributed scatter over streams, or it could be, well, I want to break apart like this graph into multiple subsets. So there's multiple scenarios in which you'd use a scatter. A gather operation, on the other hand, is very useful whenever you're doing something like synchronizing data. So basically, let's say you have different weights for 10 different models that are trained in a data parallel way, and you need to make sure that they all have let's say they have sorry, like let's say you're doing a gradient update, and these 10 models and on these 10 different machines each have their own gradient update weights. So what you do is you gather these 10 different weights, and maybe you take an average of them, you take a max of them, you do whatever, like whatever you want, like basically. So that's why the gather reduce paradigm makes a lot of sense, right? Um, and so yeah, and then sort of I guess like the giga most complicated version of this is the all gather. So although I don't know when this would be used exactly, I need to think about it a bit. But this is sort of like the like more of the all-to-all communication patterns where okay, like they each have different subset of the data, and then you want everyone to have all of the data. So this is where an all gather would be very helpful. So again, really, what matters is you're sending data, which is your input, your outputs, your model weights, and your gradient updates. So this is the data you're working with deep learning. And depending on what you're doing, either you would use a gather, all scatter, and then a reduce operation. And the backends that you're using for this are either MPI, which is very good for your CPUs, NCCL, which is what's used for GPUs, or Glue, which is a Facebook library that combines both, so abstracts them away from you. And I would bet that Pytorch actually uses Glue under the hood. So yeah, I think that was it. I know this was like more of a high level talk, but again, because distributed learning is a bit complex to sort of set up in a tutorial setting, for the most part, I think you're not gonna really use this. I think if you're just want to get speed ups from 8 GPUs that you allocated on AWS, just use data parallel. You should be good to go. You're gonna run blazingly fast. So yeah, this was my second video for today. I think the next video I'm probably gonna do is gonna be on like it's gonna be the podcast on Clubhouse on semiconductors with Bharat from Sundar. So I hope you're gonna enjoy that. And otherwise, I'm giving talks next week, so stay tuned for those. And if you enjoyed this, please subscribe. It helps me know that you found this to be useful. Thank you so much, everyone. I really appreciate it.